Hello everyone, this is Stuart Mason with a Math 156 script. Today we're talking about sampling distributions. First we're going to be discussing the sampling distribution of a Bernoulli distribution. In this case we're talking about tossing a fair coin. We're going to call heads a success and tails a failure. So you have a 50% chance of getting 0, failure, 50% chance of getting 1, success. So these are all of our possible outcomes for a single trial. 0 and 1 each occurs once because they're equally likely. And we're going to be talking about 10 throws of our Bernoulli. So we're sampling from the Bernoulli distribution 10 times. The question is, every time you sample from a Bernoulli distribution 10 times, you can come up with an estimate of the true probability, which is just going to be count up your number of successes and divide by your samples, in this case 10. That's not going to work exactly right every time. Sometimes it'll be 0.5, but it's pretty likely that it could be 0.4 or 0.6 or 0.3, and there's an outside chance that you could get exactly 1 or exactly 0. And so what we're curious about is, what is the likelihood of observing different values of our p estimate? And that's what the sampling distribution is. So the first thing we're going to do is come up with every possible outcome of our experiment. So how many different ways can you get all zeros? How many different ways can you get 5 zeros? How many different ways can you get 6 zeros? We're going to do that by saying expand.grid with 10 copies of y. And sure enough, this is every combination of zeros and ones that can occur 10 times. If we take row means, that's going to take the average across each of these rows, which will give us a vector of probabilities. So you see in the most extreme case where we flip a coin 10 times and get 10 tails, we get 0.0 as our estimate, but that can only happen once. It's much more possible that we'll get 0.4 or 0.5. You see that in the middle, those are quite common, and then at the end, the other side, we have the most extreme example of getting exactly 10 heads, which can also only occur one way. We can tabulate x to tell us exactly how frequently each of these things occur. These should be recognizable as binomial coefficients. And if we bar plot it, we see that, yes, we're much more likely to observe values around 0.4, 0.6, and much less likely to get 0.1 or 0.9. Here's a vocab term. Standard error is basically the standard deviation of a sampling distribution. So if you think of the mean of a sampling distribution as an estimate for our statistic, then the standard error is an estimate for the spread of that. Also, Paul points out a second way to calculate this. The variance of a Bernoulli distribution is p times 1 minus p, and 10 independent samples, we can get the variance by dividing the global sample by 10. And of course, this is intuitively nice because this means that as we take more and more samples, our error will shrink. Paul points out that the sum of Bernoulli trials is really just a binomial distribution. So this dbinom function will give us the density probability of computing different values with 10 trials and a probability of 0.5. So we're saying, give us a vector of 10 probabilities. How likely is it to get 11? How likely is it to get 2, 3, 4, 5, 6? If you're doing 10 trials with a probability of success of 0.5. And this will give us a bunch of different probabilities. You see the ones in the middle are the most likely. And if we multiply by 1024, this is the length of our original x vector. This will turn these probabilities into counts, and we'll get the exact same bar plot as we did before. Of course, in the real world, we usually don't know the exact sampling distribution, but we can approximate it by running an experiment multiple times with a computer. So we're still going to be taking 10 samples, but of those 10 samples, we're going to run the entire experiment 50 times. So we've got n equals 50 and a numeric vector called myMeans where we're going to store our results, and we're going to run a for loop. In the for loop, we're going to use the R binom as in random binomial function to simulate our experiment. So n is going to be the number of trials we want, 1 is going to be the number of outcomes in each trial, and 0.5 is our probability of success. Paul's being a little cute here. He's using R binom for one trial, which basically is a Bernoulli. Let's take a look at what one of these looks like. So you see you get 10 samples. Each result is going to be between 0 and 1, and 0s come up half the time, 1s come up half the time. Let's run all that code and look at the resultant vector. Paul gives us some code to make a nice dot plot. So this shows us exactly how many counts we observed. Each of our p-values, you see 0.4 occurred maybe a disproportionate amount of time. We can add the axes as counts. And if we make a bar plot, you see it's the same shape, the same data, although it's a little bit less clear how many times exactly each observation occurred. Now Paul points out we actually don't need a for loop. This is one of the things that's really nice about R. So instead of saying, hey, give me 10 draws at 1 toss each, we can say, give me 50 draws at 10 tosses each. So let's make n 50 and take a look at the result of just this code. So now these numbers are taking values between 0 and 10, with 5 being most likely, and 2 coming up occasionally, 8 coming up occasionally, although 0s, 1s, 9s, and 10s look like they're not frequent enough to happen in these examples. And then if we divide each one of these by 10, we're going to get our probabilities, which is the equivalent of averaging each of the 10 trials. Store that in a vector called x, and we can again make another chart as before. To be complete, Paul shows that we can also do this without using built-in binomial functions. Basically, he's doing it the hard way on purpose, but instead of using binomial functions, we can sample our outcome vector originally, right, which is 0 and 1. Say we want 10 samples, allow it to replace so we can get heads and tails multiple times each. You see, again, we get a vector of 0s and 1s occurring with relatively equal frequency. And we can run this simulation 50 times. Probably worth pointing out that another thing we could do is sample the original expand out grid of 10 y's, but a lot of different ways to skin a cat. And there's our chart again. Now, without having the true distribution, we don't know exactly what p is, so the best thing we can get is an estimate of the standard error, which Paul's calling se.hat. This is a common convention. And you see it's not quite the same as the true standard error, but if we do 5,000 experiments instead of 50, we get a much closer estimate, and that's comforting. On to topic 2. So we've got a very small population, and we're going to talk about sampling from this. This is our distribution. 3 a quarter of the time, 4 a quarter of the time, 6 half the time. This is our mean. Here's our population variance. So all the different ways that you can draw 2 samples from y look like this. There's 16 of them, and these are each equally likely to happen. So these are all the different means that can result from our sampling. These are all of our different estimates of the true mean, basically, that we could get. And each of them is equally likely to come up. And we can look at what the distribution of that is. And again, the definition of standard error hasn't changed, although its utility may have. And here's what happens with samples of size 8. So you see we still have a pretty wide spread here, although we're much more likely to get something around the true mean of 4.75. And our standard error. This is the true sampling distribution, which is often infeasible to compute in reality. So Paul points out that what we could do is bootstrap a sample of 65,536 samples of size 8 and see what sort of approximate sampling distribution that we get that looks very similar to the exact sampling distribution. And with that many experiments, we do get a pretty good estimate. And we also get a good estimate of the standard error. Although notice that before it was exactly the same because we were working with the exact distribution, and here it's a little bit off because of random chance. And finally, Paul is going to row bind these tables together, so let's take a look at them individually first. Tabulate all the possible means. Tabulate our samples. And stack them. So R bind is just row bind. The tables have been stacked. And we can bar plot them, telling R that we want to see them beside each other, so beside equals true, and color one red and one blue. And you see that we get basically that our true distribution and our sampling distribution come out to be very similar. So I hope this was helpful, and I'll see you guys on Wednesday.